Welcome to the fourth week of the Artificial and Tech Talk series organized by Trinet Innovations Private Limited. I am Devin Javadana, your host for today. We already conducted 3 valuable sessions along with quizzes and competitions related to artificial intelligence and other cutting edge technologies. Just last week, we brought you a session with Dr. Noel W. Pins on artificial intelligence and its applications in uh, neuroengineering. And for today's session, we wanted to give you a glance at the interesting world of robotics and how AI is reshaping the field of robotics. Let me welcome our guest speaker and resource person for today, Mr. Kanishka Vijayasegara. Mr. Kanishka is a passionate robotics engineer, a researcher, and an AI enthusiast with a sound knowledge in AI and robotics. He gained his bachelor's from University of Moratuwa in 2018, and he has contributed to many projects in AI, robotics, and many other engineering fields. He is currently extending his services as a senior robotics engineer at Zone 24/7. I would like to welcome Mr. Kanishka on behalf of our Trinet family. Mr. Kanishka, first of all, can you explain a bit about your journey with us?
Yes, sure. Hope you all can hear me.
Yes.
Yeah. Okay. So as Devin mentioned, I graduated from University of Moratuwa, Faculty of Engineering, Department of Electronic and Telecommunication back in 2018. So the way I entered the robotics field, of course, during the undergraduate life, of course, as like most of the other people. So me and another team, we were involved in taking part in different robotics competitions during our uni life, of course, basic robotics. But after that, when I graduated, I was like throughout my graduation, I mean the undergraduate life, I have been following most of those control systems, robotics. I was passionate about that field. So right after graduation, I got an offer from Zone 24/7 as a robotics engineer. So there I started my first job as a robotics engineer, and then we continued. So at Zone 24/7 we do a lot of research on robotics, and we make robots at Sri Lanka, if you have not heard before. So from that point, even after getting to the industry, I had to learn a lot because the industry robotics is very different from the things that we do at usually in the undergraduate life. So here I am today after a few years, after learning a lot from the industry itself and building some amazing robots. Yeah, that's about it.
Thank you very much, Mr. Kanishka. And with that, I would like to hand over the session to Mr. Kanishka.
Yes. Okay. Thank you, David. So first of all, I will need a bit of feedback from the audience. Usually I do this at sessions. So I want you all to type. I want to get an idea that what kind of an audience that I'm addressing. So can you all type in the chat that what is your field? If you're a student, if you are a software engineering student, electronic student, I mean, if you're in the business side, business engineering or something like that, can you all quickly type? Quickly. If you're a software engineering student, I'm a software engineering student. That's all. It's 2 words. Or even if you can switch on the mic, you can talk as well.
So I think most of the attendees are from university undergraduates and students. So most percentages.
Okay, so from software engineering, right? Yeah, I'm getting answers. Great. I need that interaction. Mechanical engineering, great. Electrical, yeah, we have an amazing audience. Great. Okay, I think we can continue to the presentation. So I will share my screen. Okay, hope you can see my screen.
Yes, sir, we can see.
Okay. Now today we are going to talk whether machines can actually be intelligent. So we know that we have been talking about these topics like robotics, artificial intelligence. Now all these things we are trying to put intelligence into machines, right? So today let's have a look at how we can put intelligence into machines. So going forward, so today I'll be talking about a basic level because we have only a very short time period. So I'll be giving the abstract level knowledge. So the rest is self-learning. So I'll guide you to take a start about the industrial robot. How to get a start, uh, first step in industrial robotics. So I'll be talking about industrial robots anatomy and what is AI and how we can apply AI to robotics. And one part of that AI that we usually apply AI in robotics is autonomous navigation in many cases. And the fourth one, how to take your first step in industrial robotics. And the last one, you are free to ask questions. I'll answer in my capacity. Okay, here we go. So hope you all have seen this robot. If you are interested in robotics, I'm pretty sure most of you have seen this robot. So this is a very dynamic robot from Boston Dynamics, a very advanced robotics research lab. And if you have not seen this robot, go to YouTube, check their uh, YouTube channel, Boston Dynamics. This is the most dynamic and intelligent robot. I would say not intelligent, the most dynamic robot I have seen in my life. So this can do backflips, jumps, and many other things. So it's very stable, and they are growing day by day. This is amazing. So this is like one of the key turning points of the robotics, the humanoid robotics. And this is also another very very significant point in robotics, because we know that we all want to use a robot at home, but we are scared. But this is a robot, this is a product which made it possible. This is a robot called Roomba. It does very simple work. What it does is it just vacuum cleans and cleans your house. But the thing about this is this was able to make it to our homes. Like millions of these robots are running today at this moment at homes and cleaning homes. Now, this is a very good point where people can gain trust about robots. Does anyone know the name of this robot? This is also a very famous robot. Yeah, this is again a robot from Amazon named Kiva. So we know that Amazon is a very large uh, online store, retail store. So we know that Amazon is keeping everything in very small spaces, and they are delivering large amounts of deliveries per day. To make this efficient, they are taking the help from these robots, and they are nailing it, right? So they just proved that robots and humans can work together and increase the efficiency of the industry by I don't know, a couple of hundred%, right? And this, I'm pretty sure that you have not heard about this. So this is a robot called Asiro, made in Sri Lanka by Zone 24/7. I'm pretty sure that you have not heard about this, but this is pure Sri Lankan work. I'll quickly explain that what this does. So we know that usually I'll go forward, and while the video plays, I'll explain. So we know that, all right. Never mind. Okay, here we go. So this is a robot where you can use to take inventory of a retail store. Now we know in most of the cases, in the so let me pause this. So in the stores, retail stores in other countries, say if it is a USA country or China or somewhere in the world, so they have very large retail stores. So taking inventory of items in the store can be very hectic. Millions of items, right? So we can't count them manually. So what this robot does is it navigates autonomously throughout the store and reads, the captures the inventory number and the location of inventory, that where this particular item is and all. So there is a lot of data, and it's very convenient if we can get this information autonomously. So we at 724/7 have made this robot. So I will explain about this robot in the coming slides as well. And yeah, so all these robots that I showed in previous slides, those are called mobile robots. What do you think a mobile robot is? A mobile robot is a robot which can move itself from one point to another. From point A to point B, it can move itself, navigate. So there are two major types of robots. The one is the manipulator type. If you have seen those robotic arms where they pick and place items, that is one type of a robot, industrial robot. The second type is mobile robots. So we are specializing in mobile robots. So I'll explain. I'll be centered in mobile robots in today's session. So if we take a mobile robot, or any robot, so we have these primary components. This is not just related to robots, even for animals and humans, this is there. So we know, number one, we are taking sensors from the environment. As a human, we have eyes and ears, nose, touch sensors. So all these sensors are there for us to take inputs from the environment. And once we have the inputs from the environment, we process that environment and we think what to do next. And then upon the decisions that we take from using the inputs from the sensors, then we put some action on the environment. To do the action on the environment, we have hands, legs, like that. So similarly, a robot has wheels, maybe legs, tracks, anything like that, any actuator in the robot. For sensors, they have cameras, touch sensors, radar sensors, sonar sensors, those kind of things are there. Additionally, we have to have some sort of a power source. As humans, what do we have? We have energization system, so where we generate energy from the food we take and also from the oxygen that we take in, right? So robots cannot do that. At least not yet. So it has to have a battery, or sometimes, if you have seen, sometimes they use engines as well as the power source of the robot. If you have seen, if you go to the Boston Dynamics YouTube channel, there'll be another robot called Big Dog, which has an engine as the power source, not a battery. So that can also be seen there. And also, obviously, we have to have a chassis, just like our skeleton as a human or any animal. Robots have to have a structure, right? So that is called the chassis. So I will quickly explain these parts so you all can get an idea about these parts. So we can see that how these things are combined with AI in the coming slide. Okay. Now, when it comes to sensors, those are some basic sensors. The people who does electrical engineering, even software engineers, and we have mechanical engineers here. So I'm pretty sure that you have heard about these sensors. Tactile sensors means touch sensors, switch sensors, and proximity to know the distance between the robot or the equipment that you use and the nearest obstacle. And also there are two important sensors called Lidar and vision and depth sensors. So those are the most important sensors that we use in our mobile robots in actual industrial applications. I will briefly explain about those as well. And we have inertial measurement units to see the the direction, the magnetometers. So those kind of things are there. And some other sensors like orientation sensors, velocity sensors, and GPS, those kind of sensors are there. All these things are used to get an input from the environment, to get an idea about the environment, because we cannot operate if we don't have an idea about the environment, right? So if we make someone if we can take all the sensors out from some person, everything, touch sensors, eyes, ears, nose, everything, and then it's very hard for that person to operate, right? So that kind of problems are there. So we have to make sure that we give enough information about the environment to the robot for it to take its own decision. And this is a Lidar sensor. So if you have heard, those are used in, most of the time, those are used in autonomous vehicles and also robots. So what this does is it has a rotating laser beam. So whenever the laser beam hits an obstacle, so this is a room, this is our Lidar. So whenever this sensor hits an obstacle, it gives us a distance from that particular point to the sensor. So we can map that in a representation, then we get an idea about the environment. So this is the same thing, but we have 16 or 8 or 16 layers of these beams. So usually this is the car, the front view, those are the side views, and this is what our computer sees in the robot's computer. This is what it sees, right? So it has to take decisions on that. Using this image, you can see that there are obstacles around the robot, right? So this is one of the very advanced and frequently used sensor in mobile robotics and autonomous cars. And this is also another very important sensor called IR sensor, a depth sensor. So here what it does is, instead, in addition to giving the RGB image, it gives us distance to each pixel in the image. So we can get an idea. I mean, why do we have two eyes? If you have ever thought, we have two eyes to perceive, to do the depth perception. So then we can get an idea that how far this obstacle is from my eyes. So similarly, these sensors give you that information to make it more comfortable for you to take decisions. So if you know this, there's a chair from this distance, you know that when to turn your robot, right? If you're moving towards that, you know when to turn your robot. Right. Now we have an idea about sensors. Now let's look at the drive system. So drive system is as simple as, if you have wheels or legs, those motors. So similarly, this robot has two wheels, right? And this has 4 wheels with independent steering. Most of these things are used in space robotics and kind of things, and agricultural robotics as well, where whenever that you have to steer in place like that. So there are many types of, because I'm not going to explain everything of those wheels. This is not related to the topic that we are going to discuss today. I'm just giving an overview on this. So likewise, we have multiple types of drive systems. Not even this, we can have legs as well. If it is a humanoid robot, we'll have legs, right? And these wheels are called mechanism wheels. So it can move in multiple directions. Right. Going forward. Okay. Now here comes I mean, we can take a start from to today's topic at this point. So now we know that we have sensors to take inputs from the environment, and once we process that input, we can give an action item to the drive system, so it will perform an action on the environment, right? So how we take this decision, how we process this information. So here, now this is a very basic mobile robot. This is something that we usually do university robotics demonstrations from our company. So this is a depth camera, as I mentioned, looking downwards in front of the robot, the flow in front of the robot. And here we have, hope you all can see my mouse point, right?
Yes, we can see.
Okay, great. So here, can anyone guess what kind of a sensor this is? So this is a Lidar sensor. As I mentioned before, there are sensors called Lidar. So this is a Lidar sensor. and we have motors as our actuators, and we have a control board, and as our brain to take the decision. Here we have a computer. Here we have kept a laptop simply. So just like that, we can have a computer take this computer to take decisions. All right, now we have the computation power as well. Sensors, actuators, and here we have the brain. Okay, now we have to tell the brain how to work, right? How to work, how it should work. So here we go. Now, now we have to take inputs from the sensors, and we have to call actions on the drive system. So there's a lot of communication, right? So how do we implement this processing part? So we can get multiple questions, like we have to drivers to get information from sensors, and also to write information to the driver system. We have to write again drivers, right? And we have to develop algorithms to take sensor information in and intelligently think and take decisions, and libraries to process. I mean, if it has vision based components, so we have to have third party libraries and all. And how are we going to develop it? Can it be a single program, or can it be a parallel processing program? So those kind of problems are there. Plenty of questions, like if you are going to build this from scratch, there'll be a lot, because this is not the simple robot that you usually build for like a line following competition or anything like that. So this will have more complex scenarios. This will not have any lines on the floor to follow. It does not have any magnetic stripes on the floor. It doesn't have any visual markers placed around the environment, so you can find your path towards a goal. So there's nothing. The robot has to be purely intelligent. It has to take the inputs same as that we animals and people get, and take decisions upon that, right? So it is going to be a very hard task. So we have to have a very robust and very good architecture to implement all these things. So so as a solution, so what we can have is we will have to have a framework kind of a thing, a middleware on top of our operating system. If we have a, now say that we have this computer, we'll obviously have an operating system, right? Windows, so Ubuntu, anything, any operating system. But to communicate with sensors and our drive system, we will have to have another layer on top of this operating system. So that people found the need of a middleware or a meta operating system to implement all these things, more like a framework. So like in time, this ROS, robot operating system, was introduced. So this is not a traditional operating system like Ubuntu or Windows. This is a meta operating system which runs on top of an operating system. So we need basically we need a Linux. Most of the time we use Linux. We need Ubuntu or any Linux distribution to run this cross the meta operating system, right? So if we talk about, I mean, at this point, take this note. So if you are to get into industrial robotics, industrial mobile robots, this is a very good start for you. I mean, one of the first things that you should have a look at and study is ROS. There are plenty of tutorials available. So search on internet as robot operating system. It will be a bit difficult. You will not see how this will be applied to robots at the beginning, but get used to it, get some simple things up and running. Then at the end, you will realize that how important this thing is. Right? And how ROS started. So early in the days, as many other, just like many other technologies at Stanford, we started as a research project, I guess a PhD project in 2007. And what they did was they made this robot as their project, and they faced all these questions that we had, right? How to get all these questions. So what they did was they came up with a framework called ROS, and they were able to successfully utilize that framework, the meta operating system, to run this robot. This is called Prototype 1, PR1. And then in 2007, they formed a company called Willow Garage. So Willow Garage took care of robot for a good 6 years, where this where Ross got very famous during that time, and that is the point where they named it as Ross also. So what they did was they evolved this. This is a very basic prototype, right? So then they came up with this robot. So this has a mobile navigatable platform. This robot can move from one point to another, and in addition to that, it has arms on it as well. So pretty much similar to a human, right? So it has 2 arms, and it has sensors just like our eyes, and also instead of legs, it has wheels. So that is the only difference. So to advance this robot from here to here, so they came up with several hardware advancements, and in addition to that, they advanced ROS as well. So we are really thankful for them for bringing up this amazing project. So we are like, there are thousands of industrial robots depending on ROS at the moment. I mean, not thousands, I would say 100,000 probably. And then in 2013, Open Source Robotics Foundation took the responsibility of ROS, and since then they have been maintaining this ROS. So one thing about ROS, now as I mentioned, this started as a research project, right? So, and also this is an open source project, so many people are contributing to this. So one thing that I personally have felt in open source projects are very good. That is a way to go forward. Everyone's contribution is important. But if you are taking an open source project to your industrial grade project, then you'll have to closely look at all the flaws of that project, because that particular person who contributed to the project may have not used it for your particular use case. So you have to make it perfect for your use case. So Open Source Robotics Foundation is now trying to make this robust as much as possible, so everyone in the industry can use it for their industrial grade project. Right. So if you have any questions, just put it in the chat. We can have a Q&A session at the end and discuss everything. All right. Now let's see that why ROS is so important and how it is going to help us. Now in ROS, I mentioned in the previous slides, I mentioned that we have to take inputs from the environment, and we have to process them and then give some action items to our robots, motor controllers and all. So there are plenty of components. So what ROS does is, ROS make all these components individually running components. I mean, those components are independently running, loosely coupled, I would say. Now, say this is my camera node, and this is my what is this? This is my decision taking node, and this is my motor controlling node. So I'm not writing everything into a single code. I'm running 3 different instances, 3 independent nodes. Those are only connected using message passing. Now, if you are a software engineer, if you have heard about MQTT and all, so probably you know that how PubSub works, right? Publish and subscribe. So this particular node takes input from the camera, and if there is any processing, it does the processing, and it sends information through a message passing mechanism. There is no code level relationship with this A and B. So it will only pass information from a message passing mechanism. So so if this can survive without this, just in case if this B can survive without a the crashing of A will not affect the rest of the system. So we'll see that part, how it works. So basically from ROS, what we can introduce is we are decreasing the amount of interdependencies. So we are not writing everything to a single code. We are chunking it out and running several independent components, right? And it is very, very easy to maintain our code base when we have a modular structure, and to add and remove functionalities. And also code reuse is there. Now imagine I'm planning to use a LiDAR X, LiDAR named X, right? So I write a package to retrieve data from this LiDAR and publish it to a ROS topic. And the rest of the application is, say that I'm taking LiDAR and I'm identifying whether someone is coming towards my robot and making a siren run. And there's another person who wants to use the same LiDAR X to make some navigation algorithm. Now, so if I have developed a package called A to get information from X LiDAR, and if I have not tightly coupled my code with the rest of the program, so I can give this A package to the other person and he can use the same package for his application without any change, right? So the code use has been magnificently increased by using ROS. All right. And also when developing with ROS, you can use like most common languages are C++ and Python. If it is a time critical work, we usually use C++. And if it is like other task, not time critical, but if we need it to be implemented fast and easily, we use Python. And also there are support for Java, Lisp, and Swift as well. But those are not very commonly used. Most common languages are C++ and Python. I think like most of the engineers now are pretty familiar with Python, right? So I think it's very easy to get started with ROS as well. Okay, now here comes a problem case. Now imagine this is my robot, and these boxes are my ROS nodes, independent nodes that I explained. Okay, and here, now imagine I'm running this component and everything is there. So one thing, so now to navigate, I need some component called map creator. So just don't think about the application, I mean, how the functionality of this robot is. So I need this person. But I'm taking inputs from LiDAR and camera both. So this is some sort of scenario like where we have, duplicate sensors. I mean, we have two. We have redundant sensors, LiDAR and camera, right? So in this case, just in case, if the LiDAR stops working, we still get the information from the camera. So if we integrated this LiDAR reading part also to the same code base, imagine crashing the LiDAR reading part will affect the entire system. But if we made it loosely coupled, if you are only passing information via messages, then of course, even if the LiDAR goes down, we still get information from camera. And if the map creator is getting enough information from the camera, it can run without any problem, right? So it will run perfectly with power planner and motor controller, and everything will work fine. And also, so imagine now I'm using a LiDAR called X. Okay, now in few years, another company makes a different LiDAR called Y with less price and more performance, and those kind of things are there. So now I want to switch this LiDAR X from LiDAR Y. Now, if I integrated this to the same code base, then I will have to get into the code base and change the code base. We know that this will be a very large code base. If we have to change a large code base, again, that's very troublesome. So in that case, if we used ROS to make these loosely coupled, so what we can do is we can write a simple ROS package only for Lidar Y and just remove this, just delete the X Lidar package and add it here. But only thing that we have to make sure is it will publish data to the same topic name, same message passing mechanism called Lidar data, and also data type should be same. If those two things are same as Lidar X, same as Lidar X, then the entire system, the rest of the system will not even notice that there was a change. I hope you all did understand that part. The importance of ROS. So these are the things that the benefits that we get from ROS. So number one is we can do hardware abstraction. So that means, as I mentioned earlier, so we can replace Lidar X from Lidar Y without notifying the other components of the system, without telling the other components. We can just start it. We can just replace it, right? Hope you all are with me, right? Any input from the audience? No input. Okay, it's all right. If you have any questions, keep it to the end. I'll answer as much as possible. Okay, here we go. And also, we are only communicating within processes with processes using message passing, and it is very easy to manage packages because we are keeping everything separately. For camera related algorithms, we keep another package. If it is a map creation algorithm, we keep it as another package. So we only have to touch that particular package to make a change. So we don't have to touch the entire code base. And also we can run these ROS nodes in different computers. Now, say that we have a robot and a central server. So if we want, we can have these nodes, LiDAR, camera, and motor controller nodes in the robot. So those will not consume much resources, not much processing and all. But for map creation and path planning, there'll be lot resource consuming. So what we can do is we can run these paths in the server, and if we have the connection, if we have Wi-Fi connection, if all these both the robot and the server is in the same network, we can run these components in different, in the server and the robot, and it will work seamlessly without any problem. It is connected using their IPs. All right. So now we get to the core of today's session. Now here, AI in robotics. Now let's first look at what is AI. Now, from what I believe, AI is the science of intelligent machines. So this is now we all talk about how we can make a machine intelligent, right? All these Turing tests and all. So we are trying to make a machine intelligent. So studying about that and everything is coming under artificial intelligence. And there's another very, very frequently asked question: is it actually artificial? Of course not. AI is not about artificial intelligence. It's all about how you rhyme it. So it's about natural intelligence. What we try to do is we try to natural intelligence into machines. I mean, we try to mimic how our brain works into a machine. Now, if you have heard about neural networks, now we try to understand how our neurons work, and we try to implement it or model it in a machine. So there is nothing called the intelligence is not artificial. The intelligence is natural. What we are trying to do is we are trying to model that intelligence artificially in a machine, right? Because in the coming slide, I'll explain it. So here, if you think about the intelligence, if you simply think about the intelligence, so there are two types of intelligence. One is logic or rule-based one. The other one is learning-based. So I'll take this as an example. Now imagine you are going somewhere where you have not been earlier, a new place, right? So then you will have to look at the boards and take decisions where to turn and all, right? So you have to intelligently think about it, take decisions. So this must be the closest route. Those kind of decisions that you have to take, think and take logically. The other one, the same route that you take to come home from office. So usually same route. So you don't have to think anything about it. Your body will automatically turn your car whenever there's a road that you have to turn. So those things are, this is in most of the, in our brain, this is how we work. There are two types. The first time, probably the first time we use logic and rule, then we learn that process. Then after some time, we learn ourselves to do it by practice, right? So in AI context, so these systems, logic and rule-based systems are called artificial cognitive systems. And learning-based ones are machine learning, the most famous intelligence type in computers, right? Machine learning. So you all think that that's the only thing about intelligence in machines, but it is not. There's another part called artificial cognitive systems as well. So if we take examples, so things like expert systems and multi-agent systems and autonomous navigation also falls under this logic and rule-based intelligence. And for machine learning, we have genetic algorithms, neural networks, regressions, everything that we train. If there's a training phase, that falls under machine learning. Right. Okay, here we go. In robotics, what kind of AI applications are used? Of course, we have navigation, right? To get from point A to point B, we have to take decisions, we have to take rules, take inputs, and we have to do the navigation. That is an intelligence in a robot. The other part is object identification. Now we have to see that if this is a person or a desk or anything like that. So that is there. And also some robots have natural language processing to take commands in. And we have multi-agent systems where we have multiple robots working to collaborative robotics to get something done. And also we have big data. At the beginning, I said that we have a robot called Zero. Now in that robot, we get enormous amount of data, large amount of data. So we can manipulate that data and arrive on some sort of patterns, right? So all these things are usually used in robotics. So if you are planning to get into robotics in the path of AI, so these are the entry points for you to take. So these are the things that you should keep your eye on and learn. Okay, here we come to the next part, autonomous navigation. Okay, now give me a second. All right, now think of a scenario where a robot has to go from point A to point B. So before that, we'll think about how a person, a human, will get from point A to point B. So imagine you were kidnapped by some set of people and you were left somewhere in a city. You are in middle of a city. Now you have to get to Colombo. So that is your destination. You know that. So what will be the first thing that you will do? Any idea? Even if you don't answer, just think about it. So imagine you are in a city that you don't know before. So you have to get to Colombo. What will you do first? Yeah. Did anyone switch on the mic? Okay, no worries. Okay, and what you will do is you will look at, yeah. Okay, no worries. I think someone tried to talk, but I didn't hear. Sachini, are you trying to give an answer? Okay, here we go. We have an right, great. Yeah, check where you are. So what you try to do is you should look at the boards and identify where you are. So that part is called localization. So any robot has to do that part. So you have to know, first of all, before going anywhere, you have to identify where you are at the moment, right? And then, so imagine you identify yourself is at Goal town right now. By looking at the board, you identify the town. Okay, now you think how you can get to Colombo from Goal. Now, obviously, there are two routes. You can take the highway or you can take the Goal road. So there are two roads. There could be other shortcuts as well, but two major paths. One is the highway path and the other path is Goal road. So then you have to identify which path to take. So then you will do a cost analysis. Now you see that how much time it will take for me to how much time it will take for me to get to Colombo from highway and Goal road, and the toll fares and right. So you will analyze that part and you will arrive on a path. So that is called path planning. You have to come and come to a decision and decide on a path that you're going to take. Right. Now imagine that okay, your kid members left your car as well. So now you have a car. Now and you decided to take the Goal road. For some reason, you by after analyzing the toll prices and all, you found that that's not like very congested time. You can take the Goal road without any problem. So you are taking the Goal road then. In that case, so when you are traveling, you have cars in front of you, you have to take turns. So for all these things, you have to look at the road. You have to perceive obstacles. You have to identify, okay, there's a car. I can't go and hit this car. I have to turn my car and go around it. And in front of the road, in front of me, there's a bench. So I have to turn. So these kind of things you have to do. This is natural navigation. This is how humans think. This is not, I mean, not coming only for robots. This, as I mentioned before, we are trying to model the natural intelligence of human and animals to machines. This is the same thing that we have done. So here what we try to do is now we need to look at obstacles and avoid obstacles, or perceive and avoid obstacles. That is also done. On the fourth one, now imagine now you come from Goal road, so in Alugam area or some area, so there's a huge traffic jam. Nothing is moving. A container has fallen, and you see that this is not going to be cleared for next 12 or 13 hours. So you know that this is not going to work. So then in that kind of a scenario, you have to get yourself, you can't stay for 12, 13 hours, right? So you have to get out of that situation. So usually say that there's no turning, there's only one lane available or something like that, then of course you will have to reverse even for kilometers. So that is also something that you will have to do in order to get over your stuck scenario, because that is better than staying for 12, 13 hours in the traffic, right? So you will have to have some methods to get out of those kind of situations, stuck scenarios where you can't move any forward in the intended path. So to get out of that, you have to have some sort of recovery behaviors. So this is the same way that we think about our navigation as humans. Probably animals have the same sensors as well, same decision process as well. So let's quickly go through these scenarios. Now, as I mentioned, ROS is a very good platform. Now, people have been contributing many algorithms on top of ROS. Once this Velo Garage laid the foundation on ROS, on top of that, people have been developing algorithms on top of ROS. So the most important algorithm is there's a navigation stack called ROS navigation stack. ROS navigation stack. This is readily available. Now you can take it and configure it with and use it in your mobile robots if you have the enough number of sensors. So what it does is it takes sensor inputs to the navigation core, and also at the same time it is using sensors to find robots location. Now we use our just as us, like we used our eyes to look at the boards and identify our location, right? And at the same time, to avoid obstacles also, we use our eyes. Similarly, cross navigation stack also does the same. And once we give a target goal, it will take this information and it will run through this entire process, and it will give us velocity commands, which way that we should travel in which speed. And we can decode these velocity commands. Velocity commands means like how fast you should go, in which direction. So we can decode this information in our motor controller and drive our motor, and we can get the feedback again to here. So that is how a simple navigation stack works. Now I'll quickly go through the important parts of a navigation stack. Number one is mapping. Now you have to have a map in your mind where you are and where you are going, right? So this can be mapped in different ways. We can have a very complex map called occupancy grid map. So here what happens is these white areas are not occupied. So where you can move. These are the roads. And imagine these are the buildings. These gray color ones are the hard obstacles. So we can map everything like this. This is very detailed. Or we can have a simple representation like some location. So we can make sure that I can go from this point to this point, this point, this point, likewise. That's all. Now from here that you have infinite number of paths. And this is also another type of mapping by using your own path only. And also it can be a very basic topology as well. If you are using line following robots in grids, probably you have seen this type of maps. You are storing this in your Arduino array. And when it comes to localization, I think we're running out of time also. So there are basically a few types of localization. So local localization, this is for the mechanical and electrical guys specifically. So local localization is just taking the odometry of the wheel. I mean, if you have turned your wheels by one round, you know that you have traveled a circumference distance. So by calculating that, by adding those rounds here and there, you can identify where you are, right? But this can be very wrong due to drifting and those kind of scenarios. So we have very advanced localization algorithms. I'll briefly tell, but you will not get a big understanding on this. So go and search on these algorithms. The first one is global algorithm. So in global algorithm, what it does is we have to give a predefined map. Now we know the map and we travel on the map. Now we know the entire Sri Lankan map, say, and we know where we are at the moment. So that is one way. And the other one is SLAM, simultaneous localization and mapping. And this is like an exploring task. Imagine that you are in a country that you have never been before, or a city. And what you do is when you are traveling, you try to remember everything, and also you try to remember where you are right now, right? So that is how we work, right? So then we can find our way back to our starting position. So when we walk forward, so we see, okay, there's a postal office here, there's a shop there, okay, I'm near the shop. So that information is with you, right? So that is how you can locate yourself. So then you have your map from the starting position to your current position. Then if you are coming back, you know the map and come back. But you don't know one point beyond your current position. You have to go forward to identify that position. So these are some algorithms. Just don't think much about it. So this is called global navigation. So as you can see, the map is given. So this map is given. This is a known map. So all I have to do is I have to locate myself. I'm here. So I just have to locate myself in this given map. This is a map. This large, the right side one is a map. So I just have to locate myself in this map. So once it starts moving, you'll see I just have to make sure that I know my position. Likewise. So that is one localization method. The other one, most common one, is SLAM, because we know in vehicles and everything, autonomous vehicles, we don't have information, the global information about the entire city, right? Because it can change time to time. So what it does is it tries to map and localize at the same time. So it will go forward and it will make the map and localize itself. So this is some sort of a chicken egg problem. So people ask, what is done first, mapping or localization? So this is done simultaneously. That is why it is called SLAM. So this is a very good area for you to do an individual study, because this is very interesting. This is how we map ourselves in some unknown city, right? Have a look at those things. So I'm just giving you high level points so you can go and search and get an understanding about this. We can't actually give everything or teach everything or gain everything in a subject in like 1.5 hours, right? So I'm just giving the brief introduction, a very abstract overlook, so you can go and just get the information. I mean, the terms, SLAM, those kind of things you have to note down and just go and search. There's a plenty of information and YouTube videos that you can watch on these topics. All right. So now we are localized. And the next one is path planning. I explained this before. So if I have obstacles like this and I'm here at point A and I have to get to point B, I will have multiple paths. Then I have to evaluate which path is the least cost one. So you can calculate the cost in different ways. Sometimes turning can be very costly for your robot. That depends on your structure and wheel configuration and everything. But it doesn't necessarily have to be the distance. Sometimes if the distance might be very short, but the road is very rough. Sometimes taking the smoother road with the larger distance will be less costly. So that totally depends on your cost calculation algorithm. You are totally free to come up with an algorithm, because in robotics, number one is algorithm. So you have to make sure that your algorithm knowledge is very good to get to this domain. All right. All right. And once you do the path planning, that is also done. And the next part is the most interesting part of navigation is perceiving obstacles. Here we have to identify obstacles. Now in humans, without any overthinking, we just detect the obstacle, right? But for robots, it's not like that. We have to develop advanced algorithms, because in our brain there are like 100,000 millions of algorithms running at the moment. But the only problem is robots will not develop its own algorithms. We have to model and develop the algorithms, right? So in this case, what it does is it makes some sort of a representation like this called occupancy representation. I mentioned this earlier also. So it takes inputs from depth cameras. This is a depth camera and Lidar, and also we can give a predefined map if we know that these walls are not going anywhere. So we can give this information as well, right? So what it does is, so whenever there is an obstacle, it marks this obstacle on the map. Now we know the robot cannot reach this point. robot's center point cannot reach this hard obstacle. So if we can make this kind of an occupancy grid or array, so we can make sure once we calculate a path, just like here, when we calculate the path, we can do the cost calculation using this map. So from here to here, there is no cost, there is no obstacle. So the robot can move from here to here. So if our path comes, our end goal is here, now the path will be something like this. Now, when calculating the path to this, like path to this point like this, we have some obstacles in between, right? So there will be a huge cost, which will exceed our threshold. So we will get a output saying that, sorry, we can't travel to this point. Then it will try to travel, if it has more information, try to come from this side by going out and coming in from another side. So that is how a robot perceives obstacles. Okay, I'm quickly going through these slides. And there we have it. We have perceived obstacles as well. And the last one is getting out of a stuck scenario, recovering a robot from a stuck scenario. So basically in ROS navigation system, this is the structure they use. So first of all, I mean, we take all the decisions using cost maps, right? We have to check the cost from point A to point B. So that is how we decide whether we can go or not. So there can be problems with cost map. There could be noise. So to make sure that there are no noise included in our cost map, first of all, what we do is we clear all the cost maps. Once we clear all the cost maps, the sensors will regenerate the cost maps as soon as we clear it. Then we can make sure there are no noises. These are actual hard obstacles. So once we clear it, if it is clear to go, it will start navigation again. And even if it is cleared, if it still gives that the robot cannot move, then what it will do is it will turn around itself. Around itself, it will turn in place rotation. So then you can see if there is another alternative path for the robot to get out from the scenario. So if that is also, if it found a way, then it's clear to go. It will take that new path to reach the next goal. And if that is also not working, it will reset everything, all the cost maps. This is just local cost maps. This will reset all the cost maps and then try again. And then again, it will try clearing rotation. If it is not also working, the robot will say there is no way for the robot to recover. But the good thing is we can write our custom packages to recover the robot. So as an example, in our case, we had written some scenarios to reverse the robot to some extent because we had sensors around the robot. We had the vision in the back as well. So we reversed and had a look at whether there are alternative paths. So you can develop your own recovery algorithms. This is all about developing algorithms. Even for path planning, localization, all these things, you can write your own algorithms, right? So if you have developed algorithms for all these four components, then you have successfully developed a navigation stack, navigation algorithm. We say complete navigation algorithm. Now this is the basic ROS navigation stack. If you search it on internet, you can get an idea about it. How they take inputs from sensors like here and other components, and also at the end of the day, after calculating all these things, it will give velocity commands to our motor controller. All right. Okay. I know that it was pretty fast, but I had to give the idea to you all about what you can do in this area. So I hope that you all go and do a search on this and get an idea. If you have any questions, I'll put my email also in the chat. You can drop me an email. And if there's any project requirement in your university or something like that, I'm depending on my availability, I'm happy to help. So drop an email if you have any further questions. If you can't ask it at the end of the session. Okay, now we'll have a quick look at how to take a start in industrial robotics. So number one, learn algorithms. So any, I mean, even for mechanical students, electrical students, electronic students, I would say, don't skip algorithms. Algorithms keep you growing. So it will keep your think scenarios, think patterns, think process. It will improve you. So learn about algorithms. Don't skip it. And software engineers and electronic and electrical engineers learn ROS as well. Okay. Those two things you have to learn. And when it comes to a robot building a robot, I mean, even for Swan 24/7 is a large company with a large team of robotics, right? So that also took more than 5 years for us to arrive at this level. So from the basic prototype, from improvements to here and there. So this is building a robot is not an overnight task, especially an industrial robot. It's a very large process because this has mechanical parts and all. So that's a large process. So you have to be patient on this. And also something that you have to learn is what I'm going to tell next. Now, usually in how many of you are in mobile app development? There are software engineers, right? A lot of software engineers. Right. I'm just checking the chat if there's anything that I can take. Okay. So for mobile phone, mobile app developers and all, when it comes to testing, what you do, you have a lot of phones that you can test on, right? You can just use a phone and test. And also, if there's something, if the app crashes, all you have to do is restart the phone. That's it, right? But in robotics, this is not practical. I would say why. So, one, we don't have plenty of robots. We don't have any amount of robots that we need, right? One reason is a prototype of this robot will cost more than a Tesla Model 3, the large amount of money for a prototype, right? So you will not have many robots. And number two, when testing a robot, if we navigate robot from point A to point B, so to do the same test again, you have to get the robot from point B to point A again. So it's not like restarting a server, restarting a mobile phone like that. You will have to take the robot back to point A and run the test again. So this is going to take very long time. So if it is very buggy, I mean, algorithms by nature is very buggy, right? There could be a lot of bugs. So, and also if this bugful algorithm goes wrong and hits some surface, I mean, some obstacle like that, and robot will get damaged. As I mentioned, the price of the robot, you probably now you understand why we can't straight away test these algorithms on a physical robot, right? So as a solution, we have to have simulation. Simulation is the key because for students also, obviously we don't have money to build a actual robot. A single Lidar will cost about $3,000, $4,000, right? Least costed one will also cost about at least $200. So that is not an amount that is affordable by a student. But fortunately, this problem is universal. Even for people in other country, it's a good bit of money. So what they have done is they have made simulators. Basically, you can test an entire robot using simulators only. But of course, there will be some adjustments when you try it on the physical robot. But I would say 95% of the development, I would say 90% of the development can be done in simulation. So basically, when you are simulating, what my suggestion is, first divide this simulation into different parts. Don't try to include every simulation into one single component. So one thing is you have to simulate mechanics and electronics, and then navigation algorithms, and the rest of the items. I mean, the user case software. state machines and how the robots is monitored, all these things you can simulate in different way, right? So these are the things that you have to try out. For mechanical, I mean, there are a few mechanical engineers, right? So probably by now you know that the capability of SolidWorks, right? You can test all the force bending moments and all the weight calculations, coupling angles, everything can be calculated using the new software. So you don't need an actual robot to do that. So we usually don't go the trial and error method in robotics. What we do is we plan well, and then only once we have a perfect robot, only we develop it. We know that when we take part in robotics competitions and all, what we do is we do the trial and error method. But industry, we don't have that luxury. We have to make sure that this is the final outcome, and then work towards that. So what we can do is we can plan everything design everything in SolidWorks and do all the simulations, coupling angles, weight simulations, everything can be done there. And also for electronic students, we have Altium, I think PSpice also there. I mean, OCAD, all these things now have the simulation capability. So you can do all the simulation, electronic component simulation there. And also, I think now SolidWorks have probably have thermal simulations as well. I'm not sure about it. So everything, the hardware wise, everything can be simulated using these softwares. So some of these softwares have free student license for universities. Check on that as well. And also for navigation, you don't need a robot at all for navigation. So there are two types of simulators that we usually use. One is a software called Gazebo, runs on top of ROS. So here you can create any type of an environment. You can model very easily. You can model a house or an office environment inside this one, and also you can make fully functional robot, including lidar sensors, uh, depth cameras, RGB cameras, everything. You can implement a fully functional robot and integrate it with ROS using Gazebo. So you don't need a robot at all to do and simulate your navigation task. Even we first go to the softwares and do simulation, then only we go to the robot. So at this point, you can write your entire software stack using this simulation. And if this is a bit resource consuming, you will need a better laptop for this. But there are some low cost, low resource consuming versions as well called Stage, which is a 2D simulation platform. So you can use that as well. All right. I know it's just a bit fast, but I don't want to crop any of it because I just wanted to give you the high level idea. You'll at least grab the terms that we discussed today. So then you'll be able to know that what kind of a scope in this area that we have in industrial robotics. I think it's time for questions.
Thank you very much, Mr. Kanishka, for that valuable session. Now it's time for the Q&A session. The participants can put their questions in the chat as well as in the Google form we just sent you. Meanwhile, I'll forward the questions from our panel to Mr. Kanishka. Mr. Kanishka, first of all, can you give us some insights about the prerequisites required for getting into robotics? Like what subjects we need to follow to get into the robotics field?
Yes, as I mentioned before, number one, if you are a software engineer and electronics engineer, so you'll be probably getting the side of algorithm development. So number one, you should excel yourself in algorithm development. You have to try out new algorithms. I mean, there are platforms that you can try out algorithms because solving algorithms is some sort of a hobby for some people. So make it your hobby. I know sometimes it's hectic when you're stuck in somewhere, but still, if you can get yourself into that hobby and practice that will be very helpful. And the other part, if your university offers control systems to take these modules, and even if not, there are plenty of online courses available on control systems and uh, yeah, control systems and algorithms. And in addition to that, ROS, uh, I think universities now teach it. Back in the day, it was not very common, but you have to learn ROS if you are planning to get into industrial robotics. And even for software engineers and uh, electronic engineers, I would say you have to have some sort of a mechanical knowledge, and vice versa. For mechanical engineers, you have to have some sort of an idea about the things that other people do, because that is because in industry we work as a group, we work as a team. So we have to have an understanding about other parties' work to get everything work and fit everything together without any problem. So there'll be very less amount of miscommunication in the industry if everyone has a good understanding about others' work. Yeah, most of these work, I mean, the content you can learn from the internet, and also not to forget, uh, keep yourself updated. Keep looking at the new inventions in the area. Keep checking on the YouTube channels that usually post. I mean, Boston Dynamics and all these common robotics platforms, information platforms. Just keep yourself on in the loop, so you'll know what are the latest technologies are, because we don't want to reinvent the wheel, right? So if we know that this is done by someone else, we can refer it to and work on that.
Yeah, thank you. The next question would be, what kind of different career paths are there in the world of robotics?
Yeah. So there are several. For mechanical engineers, obviously, the mechanical design and simulation is there. So you can take that path. And for electrical and electronic engineers, obviously, there's another set of motor controlling, control systems, and PCB designing. All these things are there. So that part is there. And in addition to that, ROS algorithm development is also there. For software engineers, there's a lot. You can either get yourself into the algorithm side, ROS navigation, and those kind of things. In addition to that, there are many components comes with robot monitoring. So because we make robots to run independently, right? So we can't expect someone to stay with the robot. So we should be able to monitor our robot remotely, and there should be dashboards for that, and also to manually control via internet just in case if we need it, and those kind of things are there. So there are many uh, control software. I mean, enterprise software also developed with this industry robotics, because we are not trying to a company will not try to sell just a hardware robot, say that okay, here you can take this, you can go and do whatever that you want with this. We have to provide a complete solution which can be handled by a non-technical person. This should be just like some ERP software. We just have to very simply click something and get things done, right? So for software engineers also, there's a, because most of the people think that okay, when it comes to robotics, okay, that's only for electronic engineers and mechanical engineers. No, it's not. I think then back then, uh, when it was research and development, maybe it was like that. But now, in the future, I would say more than 50% will be with software engineering.
Yeah, okay, there's another question. Uh, can you explain a bit about the current demand that we have for robotics in Sri Lanka as well as in the world?
Right. Uh, Unfortunately, I don't have a chart, but I'll explain why this was written in past 2 years. Now we know that many companies faced a lot of problems due to manual labor. This is not a good thing, but unfortunately, this is the truth. So many companies had this problem because in countries like, I mean, in Asian countries, sometimes using human labor is cheaper than machines, obviously. So it was like that. But during this pandemic and all, so they realized, now if we keep two people here and there like this, so there's a huge chance of getting these infections and all. So there was a huge problem where we didn't, they had to close down many plants due to this problem. So now they are looking at the options of implementing autonomous things, at least. I mean, not to cut down, because no one is trying to cut down manual labor, because that we need to survive the society, right? Survive in the society. So in the expansions, I mean, when they're trying to expand the factory, so what they can do is, in between humans, they can utilize robots as well. So there are bottlenecks that we can't get humans to do the work. So those kind of areas they are planning to into. So due to this issue, there's a huge demand at the moment, because they want to keep up and running all these things, even during pandemics and all. If it was fully automated, at least half automated, they could have operated in half capacity at least. So that is there. So we know that manipulators, robot arms and everything is very common. Now, even in Sri Lankan companies, there's a lot. At least if it is, most of the time, at least, is half automated, half human, half automated. So that kind of thing is there. But these mobile robots, the mobile robot base robots where they can move here and there, these are a bit new. So this is a growing demand for that as well. So in Sri Lanka and all the other countries, in Sri Lanka, I would say now there are a few companies starting their robotics research and everything. So we can expect a good amount of jobs as well. In abroad, of course, there are plenty of jobs.
There's another question from the audience. Are there any projects that we can join as interns in this stage just to get experiences?
Yeah, y'all can contact me via my email address. Let me put it in the chat. So if there is anything coming up, just keep me updated and send me some information whether you are interested, if you are interested in the area. So I can open up to you if there is any. So I have sent it to the chat. So if you have any interest in joining some sort of a project, so yeah, drop me an email.
Another question from the audience. How to start or create the path of robotics and control systems? And can you suggest any online courses?
Right now, I don't get any specific course name to my mind. So first thing that you can start is, if you have worked with, I mean, the basic robotics, the sensors and all, I mean, line following robots and all, if you have done that part, you can straight away, I can suggest. But if you are very new, I would suggest get your hands dirty making a robot. I mean, we know that no one is going to use an Arduino based robot in the industry, right? So you'll have very advanced components. But I would say that's a good start. If you have not used any sort of a robotics thing, so you can make a small robot, and then if you are done with that, if you are familiar with that part, then you can straight away start with ROS. Now, ROS tutorials, you can go to ROS.org, and let me put that link as well. So there'll be a set of tutorials from starting very, very basic level. All you have to do is you have to install Ubuntu OS and then install ROS and then get started with ROS. And then right after ROS, start with the Gazebo simulation. Then you can get an idea about mobile robotics. So after that, you will figure out the path with the problems that you face. So that is how you should grow. Because I'm a person who strongly believe that uh, doing courses without any problem is not going to be effective. So I believe if you try to do something by yourself, very hard to get yourself started to this started. But if you can do that, then what you can do is when you try to think of a hypothetical scenario that where you need a robot or something like that, then try to develop it in a simulation, right? Then you will face large amount of problems. Then try to solve that. At the end of the day, if you have successfully solved that solution, you're pretty up to the standard with the industry.
We have another question. Uh, what are the terms robots and humanoids mean? What are the differences between them?
Humanoids, or humans?
Humanoid.
Okay, so it's like this. Now, when it comes to robots, so when I say the term robots, most of the people think a robot has to have two hands, two legs, and a head sort of a thing, and like that. So that is the image an ordinary person has about a robot. But actually, it's not like that. The small robot, that small cylindrical robot called Roomba, is also a robot. So people will not may not be able to agree on that, but that is a robot. So a robot is something that mimics and some intelligence. A machine, it intelligence. Sometimes it doesn't have to move also. So usually it moves most of the time. So I would say when it comes to humanoid robots and robots, there are so humanoid robots example Atlas, Asimo, those kind of things. Other robots, anything, robot arm, Kuka arm, and Fanak, uh, and also Zero, Kiva. All these things are non-humanoid robots. So you can, when trying to compare these two things, simply it is if you are trying to mimic a person, a human, if you are trying to make a human-like robot, if you are trying to make a robot as close as much as possible to a human, that is called a humanoid robot. If it has to have legs to walk and hands to pick up things and respond to voice commands and those things, most of the time, this is called a humanoid robot.
Okay. If you have further questions, you can still put in the chat because that's the last bit of questions we received.
Yeah, and also adding to that the humanoid question. So in most of the industrial applications, we don't try to solve them using humanoid robots, because we try to keep it simple as possible. Because if we need to move from point A to point B, it doesn't matter whether we use legs or wheels, right? But wheels are very easy than legs. So we don't try to make things complicated by introducing humanoids, because humanoid robots are at the moment are currently focused on R&D side, research and development. Obviously, they will have a very good future. They will do many industrial work and other things as well. I mean, care robots and those kind of things in the future. But at the moment, when it comes to industrial robotics, the majority is run by mobile robots. Not the humanoid robots.
Yeah. Thank you very much, Mr. Kanishka Vijayasekar, for sharing your valuable insights and knowledge with us. And thank you everyone who joined today with us for our session.